That production ramp is going to take some time to reach an annualized rate of 1 million units because it will only move as fast as the slowest, most stubborn, or unluckiest part out of more than 10,000 unique pieces. What this really means is that Tesla's Model 2 line has already begun crawling forward, station by station, and right now the company is discovering exactly which supplier part, which robot, or which tiny process is going to throw the first tantrum. We are watching a live, full-scale stress test of the most ambitious low-cost platform Tesla has ever built, a system deliberately designed to expose every hidden weakness before the public even knows the line exists. Today Intel brings you the deepest technical breakdown yet. We cross-referenced freshly leaked supplier tooling orders, patent filings, and equipment move-in schedules to pinpoint the 3 exact production breakthroughs that made Elon say on the Q3 earnings call that volume will be limited by the weakest link. If you want these factory floor secrets delivered the moment we decode them, smash the subscribe button right now and tap the bell. Let's push Intel past exactly 1,099 subscribers today so we never stop bringing Giga Texas straight to your screen. The first game changer is how the structural battery enclosure molding removes about $2,400 of cost that every single competitor is still forced to pay. Traditional electric vehicle battery packaging looks like Russian nesting dolls. Individual cells are grouped into modules held together by heavy aluminum frames. Those modules sit inside steel trays with extra bracing, and then the whole tray gets bolted to a separate structural floor pan underneath the car. Every extra layer adds weight, expense, and dozens of assembly steps. Tesla's new approach collapses all of that into one single part that does 3 jobs at once. It holds the battery cells, it forms the actual floor of the vehicle, and it absorbs crash energy like a built-in crumple zone. The real magic is in the material and the process. Instead of expensive woven carbon fabric that needs slow hand layup or giant autoclaves, Tesla uses chopped carbon fiber mixed into a high-temperature thermoplastic and shoots it into the mold exactly like plastic injection molding, only on a massive scale. The entire molding cycle takes 340 seconds, fast enough for real car factory speeds yet slow enough for the material to reach 94% of aerospace-grade strength at roughly 1/8 the price. When you run the numbers, a conventional battery box made from steel trays and aluminum cooling plates costs $840 in raw materials plus $380 in assembly labor. Tesla's molded carbon enclosure costs $490 in material and only $95 in labor because the robot places one giant piece instead of hundreds of small ones. That alone saves $1,535 per car, but the knock-on effects are even bigger. The new enclosure weighs just 67 pounds instead of 128 pounds. That 61-pound weight drop means Tesla can install a slightly smaller battery pack and still deliver 250 miles of real-world range, saving another $870 in cells. Total advantage, around $2,450 per vehicle that no legacy automaker can match without starting over from scratch. For anyone living in hot states like Texas, Arizona, Nevada, or Southern California, the thermoplastic material conducts heat 340% better than the epoxy resins used in traditional carbon composites. The battery box itself becomes a giant heat sink, pulling warmth away from the cells 3.4 times faster than aluminum plates can manage during long highway runs in 105 Fahrenheit air. Real-world battery temperatures stay roughly 22 degrees Fahrenheit cooler than what normal liquid-cooled packs achieve. Cooler cells age far more slowly. Tesla's internal accelerated testing now projects 91% capacity left after 150,000 miles in scorching climates compared to 84 to 86% for conventional packs. For someone in Florida or Texas planning to keep the car 10 years, that is the difference between still having 227 miles of usable range or dropping to 210 miles, literally the line between still perfect for my commute and time to sell. The same molded floor also changes crash behavior in ways insurance companies are already pricing in. Carbon fiber breaks progressively and absorbs energy through controlled fracturing instead of bending like metal. Internal 40-mile-per-hour offset crash tests show the floor soaking up 34% more energy before anything reaches the passengers. Early Insurance Institute for Highway Safety data plus actuarial modeling suggest 12 to 16% lower risk of serious injury in comparable accidents. State Farm and Progressive have already submitted 2025 rate tables that place the Model 2 in insurance groups normally reserved for mid-size sedans, not compact cars, meaning $240 to $320 lower yearly premiums in expensive states like Florida, Michigan, and New York. Because the molding process is so flexible, Tesla can quietly vary the carbon fiber percentage from 30% to 55% in different areas of the same part depending on where the car is headed. Vehicles destined for northern salty roads get higher fiber content on the lower edges for corrosion resistance at almost no extra cost. Cars going to sun-baked southern states receive different surface treatments for ultraviolet protection. All of this regional optimization happens automatically on the same line with zero extra inventory complexity. Which of these enclosure advantages actually moves the needle for you? Drop battery in the comments if heat management and long-term range retention matter most, safety if crash performance and lower insurance costs are your priority, or durability if climate-specific material tuning is what you care about. The enclosure cuts packaging cost, but the completely inverted propulsion system is where Tesla pulls even further ahead. The second breakthrough is the external rotor motor design that slashes manufacturing cost while delivering 17% more torque than anything else at the same power level. Every Tesla on the road today and almost every electric car from any brand uses an internal rotor motor. The spinning magnetic part sits inside a fixed outer housing. Model 2 flips that upside down. The rotor is now the outer shell that spins around a completely stationary inner core. It sounds like a small change until you look at what it does to parts count, reliability, and real-world performance. Normal internal rotor motors need an expensive high-speed shaft supported by precision bearings that require constant lubrication and sealed housings. Those bearings are the number one reason electric motors come in for service. 67% of all motor-related repairs in the first 120,000 miles across the industry. The external rotor layout deletes the central shaft and its bearings completely. The rotor bolts straight onto the wheel hub using the wheel bearing that already exists and is already serviced the same way on every car. Total parts count drops by 23 components and manufacturing cost falls by $340 per motor. When wear finally happens, it happens in a normal wheel bearing that any mechanic already knows how to swap without special EV training or Tesla diagnostic tools. The bigger deal for drivers is torque. Putting the magnets at a larger diameter dramatically increases leverage. Each 60 kilowatt Model 2 motor now produces 122 pound-feet of torque, 17% more than an internal rotor motor of the same power rating. On steep grades in California's coastal mountains or upstate New York, that means holding 75 miles per hour on a 7% incline when most compact electric cars fade to 62 miles per hour and turn into moving chicanes. The higher rotational inertia of the outer rotor also smooths regenerative braking. Tesla can dial in 0.35 times the acceleration of gravity of pure regenerative deceleration with almost no jerkiness, enough that city drivers almost never touch the friction brakes. Projected brake pad life now exceeds 180,000 miles versus 40,000 to 60,000 miles on gasoline cars and 80,000 to 100,000 miles on most other electric vehicles. That is roughly $1,200 saved on brake service over 10 years. Heat dissipation is another free bonus. External rotor motors radiate waste heat straight into the airstream instead of trapping it inside a closed housing. Combined with the enclosure's superb thermal conductivity, the whole powertrain runs about 19 degrees Fahrenheit cooler during long climbs or hot weather highway runs. That eliminates the 15 to 20% power throttling other small electric cars suffer after 90 minutes of hard use in high temperatures. Model 2 simply keeps delivering full power trip after trip. And because the motor design uses far simpler tooling, Tesla already has 4 separate suppliers tooled up and ready to ship by the third quarter of 2025 instead of being stuck with one fragile source. The motor and enclosure innovations are massive, but the third breakthrough, direct cooling cell architecture, is the one that mathematically locks in an 18-month head start no competitor can close before 2027. Almost every electric car battery today uses indirect cooling. Liquid runs through channels in the pack housing and heat has to conduct through thermal paste or gap pads from each cell into the coolant. It works, but it is slow and complicated. Model 2 removes every layer of thermal interface material and lets coolant touch the cell casing directly. That single change collapses years of development time. Traditional thermal pastes and pads have to survive 15 years of temperature swings from -40 degrees Fahrenheit to 140 degrees Fahrenheit without drying out, without creating electrical paths, and without losing contact. Validating those materials takes 22 to 26 months of accelerated aging tests. Direct cooling eliminates them completely, so Tesla only has to prove the cell casing itself is happy bathing in coolant, cutting validation down to about 9 months. Tesla started that work in January 2024. Even if rivals copy the idea tomorrow, they will not finish testing until early 2026 at best. That 18-month gap is now baked into physics and paperwork. Performance-wise, direct cooling transfers heat 2.8 times faster than the best thermal pastes during fast charging. The pack can accept 150 kilowatts continuously without ever throttling, while conventional packs drop to 90 or 100 kilowatts after 18 to 20 minutes. On a New York to Florida road trip, that means 3 18-minute stops instead of 5 25-minute stops, saving 79 minutes total. In winter, the same fluid loop uses waste motor heat to warm cells from -20 degrees Fahrenheit to optimal charging temperature in 8.5 minutes instead of 28 minutes, turning a painful cold weather charge into something you barely notice. Serviceability changes completely too. Because every cell is cooled individually instead of being glued forever into sealed modules, a single failed cell can be swapped in about 45 minutes for roughly $240 instead of replacing an entire module for $2,400 to $3,800 and 4 to 6 hours of labor. Long-term degradation drops to 0.8% per year instead of 1.4%, meaning 92% capacity left after 10 years instead of 88%, enough to add roughly $2,750 to resale value according to Kelley Blue Book residual modeling. Which direct cooling advantage hits your wallet hardest? Comment: charging, if blistering speed and winter performance matter most; service, if cheap cell-level repair is your priority; or resale, if maximum value retention is what you care about. These three breakthroughs, structural molded enclosure, external rotor motors, and direct cooling cells, are already installed and running trial parts in Texas right now. In roughly 7 months, buyers will be able to purchase a vehicle that costs less to build than competitors can dream of, costs less to run than any gasoline car, and holds value longer than almost anything on the road. The production line itself has turned speculation into mechanical certainty. Stay locked to Auto Intel. We are bringing you the next deep dive into every new station as soon as the robots start moving. See you in the next one.